Hello everyone. Now in this video we will discuss the Borsuk Ulam theorem. So now we have a brain teaser problem. Now if we have a bounded polygonal region A in the plane R2 and we want to prove that there exists a straight line which bisects the area of the polygonal region A in half. Then we simply take f of c, the area of that part of A that lies below the line y is equal to c. And since we know f of c is a continuous function of c, so by intermediate value theorem we can always find a value of c such that fc is equal to half of the area of A. That means we always find a line y is equal to c which bisects that bounded polygonal region in half. But let us complicate the problem. If we take two regions, let us say A1 and A2, and we are asked to find a single line that bisects each of them, then this is not quite obvious to find such a line. So, but in fact, such a line always exists. And this is an application of Borsuk Ulam theorem. So first of all, we will do Borsuk Ulam theorem, and then we do this application of the theorem. So for that, we have to define firstly antipode preserving map. So what is antipode and antipode preserving maps? So let X is a point of Sn, the n sphere, and then its antipode is the point minus X. And if we take a map H from Sn to Sm, say, then it will be called antipode preserving map. If H of minus X, this is equal to minus Hx, which means image of the antipode of X, this is antipode of image of X under the mapping H for all X in Sn. Then we say this is antipode preserving map. Now we prove that if we have a continuous antipode preserving map of S1 into itself, then that mapping cannot be null homotopic. So if H is S1 to S1, if this is continuous antipode preserving map, then H cannot be null homotopic. So we will prove this theorem in 3 steps. Firstly, we take B naught to be the point 1, 0 of S1, and we take a mapping rho from S1 to S1, and this rho is just a rotation which maps HB naught to B naught. So this is a rotation which maps HB naught to B naught. So now because this mapping rho, this is just a rotation of S1 to S1, so it is antipode preserving map. And H is given to us that it is antipode preserving map. So it means the composition rho circle H, that is also antipode preserving. Now if we take H is homotopic to constant map, which means if we assume that H is null homotopic, that means H is homotopic to constant map, and suppose capital H is the homotopy between H and the constant map, then rho circle H, that is also homotopic to constant map. And the rho circle capital H map, this will be the homotopy between rho circle H and constant map. So here we are saying that if we define rho to be the rotation which maps HB naught to B naught, then then rho circle H, that will be antipode preserving map, and that will be homotopic to constant map if H is constant map. So it is sufficient to prove the theorem under this additional condition that H of B naught is equal to B naught. Because if we prove the theorem for the mapping H, which is continuous antipode preserving map and which maps B naught to B naught, then the result can be also proved for the general case where H is only continuous and antipode preserving map. Because if H of B naught is not equal to B naught, then defining this type of mapping uh, rho circle H will be a continuous and antipode preserving map such that rho circle H at B naught is equal to B naught. And if rho circle, if this result is true for that particular map which maps B naught to B naught, then the result will be true for rho circle H. That means rho circle H is not null homotopic. But if rho circle H is not null homotopic, that means H is not null homotopic, because we are saying that if H is a homotopic to constant map, then rho circle H is also homotopic to constant map. So we will prove this theorem under the additional condition that H of B naught is equal to B naught. And we will prove the result in 3 steps. So the first step is, if we define a mapping Q from S1 to S1 by QZ is equal to Z square, then we prove here that there exists a mapping K such that Q circle H is equal to K circle Q. So this mapping Q basically maps this type of point cos theta sine theta to the point cos 2 theta sine 2 theta. And here we can see that the inverse image of any point of S1 under this Q, that consists of two antipodal points, Z and minus Z. Because if we take this point cos 2 theta sine 2 theta, let us say this is Y, then inverse image of this point, that will be cos theta sine theta as well as minus cos theta minus sine theta. So inverse image of any point of S1 under this Q, that is two antipodal points, Z and minus Z of the circle S1. And secondly, we can see that this mapping Q, this is a quotient map, and because this is basically continuous, surjective and closed map. And this is not injective because two different points Z and minus Z, they have same image. And this one more thing, Q is quotient map, and this is not injective because Q of Z is equal to Q of minus Z because of the definition QZ is equal to Z square. And also one more thing we can see about the given mapping H, that H of minus Z, that is minus HZ, because H is given to us the antipode preserving map. So because of these two, we can see that Q of H minus Z, this is Q of HZ. So it means Q circle H. Now we have these type of mappings. Now we have this S1 to S1, we have H, Now we have this Q mapping from S1 to S1, which is a quotient map. Now this is also quotient map from S1 to S1. So there exists a mapping K. So because of this Q circle H, this induces basically a continuous map K from S1 to S1 such that this diagram of arrows, this is a commutative diagram, which means Q circle H is equal to K circle Q. So there exists this type of K mapping. And we can now notice that Q of B naught, this is B naught, because we have taken that B naught is the point 1 0 of the circle, and QZ is equal to Z square, which maps B naught to B naught. And similarly H of B naught, that is B naught, that we have assumed the additional condition. So it means K of B naught, that is also B naught, because of this condition Q circle H is equal to K circle Q. And one more thing we can notice that H of minus B naught, this is minus B naught, because H is a antipode preserving map. Now we come to second step. Now in this step, we will prove that the homomorphism K star, which is induced by this mapping K, that is non-trivial. So we will prove here that the mapping K star, which is actually a homomorphism from the fundamental group of S1 to itself, this is non-trivial. Basically, we will prove here that this K star is injective map, and being injective, it will be non-trivial because it is from Z to Z, from infinite group to infinite group. So now here, we have already proved that the mapping Q, which we have defined in step 1 from S1 to S1 defined by Z goes to Z scale, this is a covering map. So if this is a covering map and if we take a path F curled from if we take a path F curl in S1, that means if we take a mapping F curl from I to S1, which is a path from, so suppose this is a path in S1 from B naught to minus B naught, then what will be F, where F is equal to Q circle F curl. Now let us take this S1 to S1. This is the given covering map Q. Now let us take this is I to S1, this is F curl, and F curl is a path from B naught to minus B naught. Now if we take F is equal to Q circle F curl, then F of 0, that will be Q circle F curl of 0. So it is Q of F curl 0. Now F curl is the path starting at B naught, so it means F curl 0 is B naught, so it is Q B naught, and Q B naught is B naught. Similarly, F1, that will be Q of F curl at 1, and F curl at 1 is minus B naught, and Q of minus B naught, that is also B naught. So we can see here that F, if we take Q circle F curl, then that will be a loop. Its starting and ending point are same. So this will be a loop. This is a loop at point B naught. So this is the basically composition Q circle F curl. So this is a loop. Now we have to prove that K star is non-trivial. So we will prove that now since this F is a loop based at point B naught, so its path homotopy class belong to pi 1 S1 B naught. So we will prove that under K star image of path homotopy class of this F, that is non-trivial. So we start this K star F. By definition, it is homotopy class of K circle F, and now we put the value of F, and that is Q circle F curl. Now because of associativity, this is K circle Q circle F curl. Now K circle Q is just Q circle H, and again we use the associativity, so it is Q circle H circle F curl. Now H circle F curl, this is a path. H circle F curl, this is path in S1 from B0 to minus B0, because H of F curl 0, this is F curl 0 is B0, so H of B0 is B0, and H of F curl at 1. So F curl is the path from B0 to minus B0, so it is minus B0. Since H is antipode preserving map, so it is minus B0. So H circle F curl, this is a path from B0 to minus B0. So basically this is non-trivial element. This H circle F curl homotopy class of this path is non-trivial element of pi 1 S1 B0. Because the trivial element basically of that group is given by the constant path based at point B0. But if we take a path which is starting from B0 and ending at minus B0, then that cannot be homotopic to the constant path, so that will be a non-trivial element. And Q circle, H circle, F curl, this is basically Q star of H circle F curl. Now Q star, this is a mapping from fundamental group of circle to itself, because Q is a mapping from S1 to S1. Now if this H circle F curl, this is a non-trivial element of S1, that means Q star of this element, that is also non-trivial element, because Q star is homomorphism from Z to Z. And if we take non-identity element of Z, then that will be mapped to non-identity element under that mapping from Z to Z, because Q is a quotient map. So this is basically non-trivial element of fundamental group of circle. So we have proved that K star F is a non-trivial element. That means there exists element in the domain whose image is non-identity element. So it means this K star is non-trivial homomorphism. So now in the final step, we will prove that H star is non-trivial, because we have to prove in this theorem that H is not null homotopic. So if we prove that H is non-trivial, then H cannot be null homotopic, because we have already proved a result that if H is null homotopic, then the homomorphism induced by H, that means H star, that is a trivial homomorphism. So we will prove that H star is non-trivial. So we prove here H star is non-trivial. Now, in the second step, we have proved that K star is non-trivial homomorphism, and basically K star is a homomorphism from Z to itself, the infinite cyclic group into itself. Now, if it is non-trivial, then it is injective. So K star is injective, and Q star is also injective, because Q star is basically induced by the mapping Q, and Q maps Z to Z square. So it is basically correspond to multiplication by 2 in the group of integers. So this is also injective map. So if these two mappings are injective, then their composition K star circle Q star, that is also injective. And we know Q star circle H star, that is equal to K star circle Q star. because we know this Q circle H is K circle Q. So Q star circle H star is injective, and if composition of two mappings is injective, then the latter one, which means H star, this is also injective. So if H star is injective, then H star cannot be trivial. So it is non-trivial. So if H star is non-trivial, then H is not null homotopic, which completes the proof. Now, the next theorem says that there is no continuous antipode preserving map from S2 to S1. No continuous antipode preserving map from S2 to S1. Now we will prove it by contradiction. Suppose there exists a continuous antipode preserving map G from S2 to S1. Let this be continuous antipode preserving map. Now we take S1 to be the equator of S2. Now we restrict this G to S1 and we take this mapping to be H. Now H will be a mapping from S1 to S1 itself. Now we are assuming that G is continuous antipode preserving map and H is its restriction. That means H is also continuous antipode preserving map. So by the previous theorem, this H is not null homotopic. Now we take E to be the upper hemisphere of S2. And we know that upper hemisphere of S2, this is basically homeomorphic to ball B2, closed ball B2. And now we have a mapping H from S1 to S1 and this G, which is a mapping from S2 to S1, if we restrict this G to E, let us say this is G dash is restriction of G to E. Then this G dash is basically a mapping from E to S1, or we can say G dash is a mapping from B2 to S1 because E is homeomorphic to B2. So we are saying basically H is a mapping from S1 to S1 and this is a continuous mapping. It has a continuous extension G dash from B2 to S1. So we have proved a result that if we have a continuous mapping H from S1 to X and it has a continuous extension from B2 to X, then this is null homotopic. But here we are saying H is a mapping from S1 to S1 which has a continuous extension G1 from B2 to S1, but still it is not null homotopic. So that is a contradiction. It means there exists no continuous antipode preserving map from S2 to S1. So now we come to Borsuk Ulam theorem, which is our main result of the section. Borsuk Ulam theorem for S2. Now this theorem says that if we have a continuous map F from S2 to R2, then there exists a point of S2 such that image of the point and image of its antipode, they are same. So for a continuous map from S2 to R2, there exists a point in S2 such that the point and its antipode, they have same images under F. Again, we will prove it by contradiction. Now suppose fx is not equal to f minus x for all x in S2. There is no such point. Now we define a mapping G from S2 to S1 by G of x is equal to fx minus f of minus x divided by its norm. Now since we are saying fx is not equal to f of minus x for any x in S2, that means their difference cannot be 0. So we can divide this by its norm, and this quantity that belongs to the circle S1, because norm of this will be equal to 1. So this G is a well-defined mapping, and of course it is continuous because F is a continuous map. So G is a continuous map from S2 to S1. And secondly, G of minus x, this is equal to minus gx. So here we are saying that G is a continuous antipode preserving map from S2 to S1, and that is a contradiction to our previous theorem. So there exists a point x in S2 such that image of x and minus x, they are same under the mapping F. So this completes the proof of Borsuk Ulam theorem. Now we have this application, the bisection theorem of Borsuk Ulam theorem. The bisection theorem says if we have two bounded polygonal regions in plane R2, then there exists a line, a single line in R2 that bisects each of them. So as I have told earlier, that if we have only one polygonal region, then it is very easy to prove by intermediate value theorem. But in case two bounded polygonal region, the proof is a little bit complicated. So here in this theorem, we take two polygonal regions, say A1 and A2. Let us denote the given bounded polygonal regions by A1 and A2 in R2 cross 1 in R3. So instead of taking bounded polygonal regions in R2, we are taking these polygonal regions in R2 cross 1, and that is a plane in space R3. And now we will show that there is a line L in this plane R2 cross 1 that bisects each of them. Now we take a point U of S2 for any U in S2. Now we consider the plane P in R3 which passes through origin that has U as its normal vector. So we take that plane P in R3 which passes through the origin, and U is normal vector of the plane P. Now this plane divides R3 into two half planes. And let us take F1U and F2U. These be those portions of the polygonal regions A1 and A2 respectively that lies on same side of P as does the vector U. Now because we are taking U in S2, so the vector U lies in one side of the plane P. So we take area of that portion of A1 which lies on that side of P where the vector U lies, that is equal to F1U, and similarly F2U is the area of the region A2. So this is area of that portion of A1 that lies on same side of P as the vector U does. Similarly, F2U, this is area of that portion of A2 that lies on same side of P as the vector U does. Now we can see that if U, now U is any point of S2. So if this U is unit vector K, then what is F1U? This is whole area A1. Because if we take U is equal to K, then the plane P, which passes through origin and which has its normal vector K, that is just xy plane. And we are taking the regions A1 and A2 in the plane R2 cross 1. So the whole of portion lies on the side of U. So it means F1U is A1 and F2U will be A2 in that case. And now if we take U is equal to minus K, then because now the normal of the plane P, that is in the reverse direction. So in the side of U, there is no area of the polygonal region A1 and A2. So it means F1U that will be 0 in this case, and F2U that is also 0. And in all other cases, if U is not equal to K as well as not equal to minus K, and all other points, for all other points U of S2, this plane P, this will intersect the plane R2 cross I, because only in the cases U is equal to K and U is equal to minus K, the plane P will be XY plane, which is parallel to the plane R2 cross 1. And in all other cases, this will be intersecting plane. This P plane will intersect the plane R2 cross 1, and that intersection portion will be a line. And that line splits R2 cross 1 into two half planes. And in that case, F1U and F2U, that will be, these will be areas of those portions of A1 and A2 respectively that lies on one side of that line, which is the intersecting line of the plane P and R2 cross 1. So, and secondly, if we replace U by minus U, then we get the other half portion of the areas. So it means we can say that F1U plus F1 of minus U, that is equal to the whole area A1. Because if we take U, if we take minus U instead of U, then we take the area of the other portion which we have left. Because we have to take the area of that portion of P which lie, that portion of we have to take the area of that portion of A1 that lies on same side of the vector U. So if we replace U by minus U, that means we are taking the area of the other side. So we can say that F1U and F1 minus U, their sum is A1. Similarly, for F2U and F2 minus U, that is A2. So now we consider a mapping F from S2 to R2 by F of U is given by small f1u, f2u. Because we know this f1u and f2u, these are areas. So area is a real number. So this basically ordered pair that belongs to R2. Now Borsuk Ulam theorem says if we have a mapping, continuous mapping from S2 to R2, then there exists a point in S2 such that image of that point and its antipodal point, they are same. So by Borsuk Ulam theorem, there exists u in S2 such that f of u is equal to f of minus u. It means f1u, f2u, this is equal to f1 minus u, f2 minus u. So it means we can say f1u is equal to f1 minus u, and secondly f2u is equal to f2 minus u. But since we have already said that f1u and f1 minus u, their sum is equal to a1, and we are saying there exists a point u for which f1u is equal to f1 minus u, which means for this point u, basically f1u is half of a1, and f2u similarly it is equal to half of a2. So we are proving here that there exists a point u in S2 such that f1u is half of a1 and f2u is half of a2. And corresponding to u in S2, we always get a line, and the line of intersection of the plane P and the plane R2 cross 1. And that line bisects the polygonal regions a1 and a2 into half, because we are taking f1u and f2u to be the areas of portions of A1 and A2. And we are saying there exists a point where this portion F1U is exactly half of A1 and F2U is exactly half of A2. It means that intersection line corresponding to this U in S2, that is our required line, which bisects both of the polygonal regions A1 and A2. And this completes the proof of this result.